Moving on, we have a keynote, system verification, solving edge computing complexity. The speaker is Ashok Chandran, who is an ADI fellow, analog devices fellow. An introduction. Ashok is a fellow at Analog Devices and a design verification director there. He sets technology direction and methodology for verification across multiple wireless communication SoCs from Analog Devices. He led deployment of advanced verification methodologies, piloting emulation and virtual prototyping for some of the most complex mixed signal SoCs at ADI. His expertise spans across circuits, software, communication systems, and application of the right tools and methodologies to enable high-performance system verification. Earlier, as part of the automotive group, he led system-level verification on multiple Blackfin DSP SoC projects and drove adoption of VMM, UVM, and formal methodologies for Analog Devices. In 2021, he was promoted to an ADI fellow for his vision, leadership, and championing of system verification within Analog Devices. Over to you, Ashok. Ashok, are you there?
Good morning. The devices that we see around us are now increasingly more autonomous, intelligent, and connected. So verifying these edge computing devices requires a focus on system verification, and that's what we will get into in today's talk. Before we jump into the presentation, a quick overview of Analog Devices. Analog Devices was founded in 1965 with headquarters at Wilmington, Massachusetts, with over 25,000 employees in 35 plus countries, 70 design centers. We serve 125,000 customers. With a strong focus on innovation, ADI has around 6,500 patents and around $1.5 billion of R&D investments per year. ADI's DNA is in the unique skills to master the physical and digital divide. We have a collective suite of capabilities that is creating a more connected, safer, and sustainable future. So the real world stimulus from the physical world is transformed into intelligent insights that go into the digital side. So that is where all of our sensors excel. So these sensors capture data in very demanding environments. These data is turned into actionable information. There are embedded algorithms that, compute algorithms that extract interesting information or insights from the data. The data is then secured and transferred in reliable and challenging environments where these devices operate. Finally, powering up and delivering efficient power solutions is also a great part of making this ecosystem possible. So we are seeing a lot of accelerating growth markets around us. Right? So vehicle electrification and autonomous transportation, they employ a wide variety of very advanced sensors and edge processing capabilities. There is also wide connectivity that we are seeing with the 4G, 5G deployments. And some of them are wired, wireless, satellite, even private networks that are being deployed. All of them are, highly, require high-end edge processing networks as well. So clinical grade healthcare requires highly precise sensors, but with a lot of intelligent algorithms built in, right? So they need to process these vital signs and extract critical parameters from them. The Industry 4.0 employs a lot of connected sensors which provide digital analytics of the operations. And finally, one of the things which are most familiar is the consumer applications, which in which a wide variety of sensors provide very excellent and immersive experiences for us. As you can see, most of these applications are banking on very advanced and complex edge computing devices. So let's look at what really is driving more intelligence into these edge devices. The one factor is the reducing the cost and power per bit of data remains very critical. We do not want to send across data over longer distances or into the cloud unless it's absolutely required. Secondly, there are a class of applications which are latency critical, or some of them are mission critical, right? Where you have to process and intelligently respond in real time. You cannot wait for intervention from a system that is far off. Thirdly, safety and security is a very important system consideration to secure both the devices and the end users. In some cases, security means that you may not want to send out data unless really required, right? So for privacy reasons, you want to process a lot of the things on the device and only send very abstracted information up the cloud. And even when you send it across, security remains extremely critical. So many other considerations also result in optimal system partitions, being beyond what can be there on a single device. These can be the thermal reasons, the device, characteristics, and many other aspects that result in this. So we do system in packages, chiplets. Sometimes multiple chips come together, or it's also a distributed system. Right? So software, analog, digital, all of them come together to form an integrated solution. And as we discussed, sometimes they extend beyond the device itself. They extend and connect to the system around it. Right? So what's in it for us in the verification side, right? What does this accelerating market provide us as a new challenge? So the critical thing to note here is that a functional full system is the goal here, which means we are tackling a whole lot of new domains, like safety, security, the software algorithms, and the and the fact that the SOC alone is no longer sufficient. So the functional system in minimal time is actually remains the goal. Right? And the other aspect that we have to consider is the time to market is really becoming much more challenging now. Right? So the market is of course more demanding. So which means that all of these pieces that we are talking together has to have a high degree of the overlap in their development. And the complete system solution, including what we talk about, the safety, the algorithms, the digital analog, as all of this has to be ready, validated, and prior to tape out, right, to build the confidence that the full system really works. So to succeed with this level of challenges, there is a growing need for actually domain and technology expertise. So we have to be technology and methodology aware, but we also need to be growingly system aware. Right? So that's where the concept of system verification comes in. So let's look at a typical system development flow where we take a product from requirements to all the way up to the customer. Right. So the requirements are formed based on market intelligence and whatever other discussion with customers. They are taken into an architecture stage, then followed by detailed specifications by hardware team, by the software team, and the system team, which kind of interacts with. There is of course interaction between all of them, and then the hardware design and all of them go into design and verification phases for their respective parts. They all come together to test and release the product for tape out, and finally product evaluation and test on the silicon qualifies it and releases to a wide variety of platforms like reference designs, ecosystem partners, to customers, and a lot of compliance and certification that also goes into the products. So we know that we are traditionally strong in design verification and software verification flows, right? That has matured over time. There's a whole little deal of things that we now understand very well in how to do this. But if you look back at the requirements to architecture, these this did we translate the requirements into the right architecture decisions? This of course has been a problem forever, but it's becoming more and more involved because the number of requirements and the complexity of the requirements is getting to be pretty high. The second aspect is whether the architectural decision is actually translated into the right software or the implementation specifications, right, for each of these domains. Of course, the other aspect is that there are multiple domains to handle, and it is very critical that all of them interpret it in the right way and come up with a common solution. Third aspect is that we go back to our goal of fully functional system on silicon arrival, which needs a right level of alignment across all of these teams, right? So the design verification process across all of them should align and also enable a lot of the product eval and test that happens post silicon. And finally, always the biggest challenge is to make sure that we did capture the requirements correctly to enable the end application, right? So the system requirement meeting the end goal is a critical need to be also tested upfront. So when the complexity of our devices rises, it is very important that our verification includes system verification. So system verification is built from the end user perspective of the system. Our goal here is to uncover issues which would have been revealed only in a post-silicon system-focused testing, or finally, or worse at a customer end, right? So that's what we're trying to avoid here. So what does that mean for us in the verification, right? So it's about how do we abstract a system requirement. This is, of course, an effort that is complementary to the verification done at the block and chip level. And it is not always that we take this effort into a platform which is, altogether different from what we do in design or, in the design verification side, right? But it is about understanding the full system and breaking it down into smaller pieces and requirements which can be applied to the standard approaches in our verification field. Right. So to get a better feel of what this kind of maps to in different of products, maybe I'll walk through a few of our products and the key challenges that we kind of look at for these edge products. The first is we'll talk about the ADI's 5G radios, which is the radioverse family of transceivers. So these are a wide range of integrated transceivers with pre-distortion and algorithmic solutions that improve and linearize power amplifiers and the overall system performance. The highly integrated analog digital software solution, which is customized to process and provide superior system performance at a optimal power to the system. And this enables a wide variety of applications like a 4G, 5G, macro, and massive MIMO beamforming base station solutions, and also enables the 5G Open RAN complete ORU solutions as well. Now, when you look at the right-hand side, where you have a transceiver, you can see that it does not work on its own. It needs to interact with a wide variety of system analog components. And that's because some of them are external filters and power amplifiers that are not amenable to integration, nor from a system placement view, they probably need to sit behind the antenna, right? So some of them are practically needs to be decoupled from the transceiver. So this means that it's actually not the transceiver alone that we need to verify. We need to make sure that its interaction with all these system components is delivering the true system performance that we are really looking forward to. So verifying a full system performance is really key here. And the second aspect is these solutions interact with complex software stack on one side. They have their own complex software stack to manage its internal functionality and also to manage the front-end analog. Right, so managing all this hardware software complexity is also really critical for us in this product. So this Analog, digital algorithms, signal processing, software, all of these are critical to make this software-defined radio possible, right? All of them, a lot of these components interact together to make this work. So verifying a true 5G system behavior is very critical in these communication products. So modeling and integrating the actual system performance checks becomes very valuable. We also need to check against standards like 3GPP to be sure that we got the solution right. And this can also very interestingly unveil very important architectural gaps as well. So 5G compliance, stimulus, system performance metrics, signal processing based debug approaches, and system component modeling, all of these are very critical to achieve verification of such platforms. So there are, of course, different ways of doing it. In some cases, the analog RF modeling is what is important. In which case, we can do this modeling in accelerated platforms like MATLAB Simulink, right? So they can do very fast simulating analog models. In which case, it becomes a co-simulation with some of these closed loop control systems. We may have to run a co-simulation with some of these external tools. In other cases, these system models can be mathematically incorporated as a MATLAB or a C-based model that can be built into our system, right? Or of course, system analog models are also possible. And these can be co-simulated with our design through DPI-based approaches, right? So there are different ways you could build in the system verification, but I think the key, of course, is to have a clear understanding of what was the requirement and the check mechanism that we need to implement here. Now, on the software side of things, the important aspect is to not just do the silicon, but also enable the ecosystem that works around the silicon, right? So there is software, GUIs, the system design that needs to happen, algorithms, and of course the product evaluation team that gets the silicon in the lab, right? All of them have to be enabled to really make the system development faster. So the high system complexity of the silicon and the software results in a typical long development time. So the software, algorithms, and the application content are all required to be actually functional. Even before, to even make the silicon usable, all of these have to be really available. So this goal has to be to enable a concurrent system development, which allows development in a native software ecosystem. This means like that we need to allow a native, interactive development environment. So the model execution speed remains very critical. So the solution here is virtual system platforms for software development and validation. Virtual system platform is a representation of the silicon and the system that sits around it using a system C modeling approach. So the goal here is that with this, we can pull the software development and verification much early in the design cycle. Even the product evaluation readiness and their lab scripts can all be made ready earlier, thereby enabling us to do a faster system release. But we also need to take this to the last mile, right? The sampling to the customer requires significant amount of software to be ready, but also to be validated. So it's a right mix of system C-based prototyping, emulation, and RTL and analog real number models that might form the optimal platform for verification of software. So the important thing is we can create the platform. That's not a problem, but it's the how do you enable the people who are using the platform? That's where the virtualizing the platform becomes very important. So the emphasis here is on providing exactly same software workflows on each platform when possible. This allows the software team to reuse, test, and debug approaches across all the platforms to be kind of uniform. And they can move test cases around platforms for faster debug. And if at all we find bring up problem in silicon, we can easily bring that back all the way up to DV software to enable triaging of these issues. Now, switching gears on to the other side of products which come under the automotive vehicle electrification solutions, right? electric vehicles represent around 2% of the worldwide electric vehicle sales, worldwide vehicle sales. But on to the next decade, we expect that the vehicle electrification will increase to over 15 times. ADI's electric vehicle solutions play into battery formation and test, battery management, and e-mobility solutions. So this EV market continues to be driven by a demand for longer range vehicles, improved safety, and decreased charge time and cost. This means that we are building complex mixed signal systems and connected systems to make this possible. So from a verification, we kind of look at a few key requirements that come up in this side of the things, which is one is a mixed signal system that we are creating. Functional safety validation remains a very critical goal. And thirdly, secure and reliable connectivity is of utmost importance. So mixed signal systems are really interesting. It is always about an intelligent trade-off between speed and accuracy, right? So these sensors form a very intertwined analog digital system, which requires very thorough system verification, right? And sometimes this is not just one chip. These are multiple of these devices and handled by a central controller that needs to be also verified. So mixed signal system verification requires adopting faster simulation techniques, and we of course know that real number modeling methodologies have now matured and very well widely adopted. So this capability that the system analog real number models give us has enabled us to bridge the simulation speed gap for complex analog digital systems, right? At least for now. The COSIMs with, of course, the analog actual simulation views still hold their place for high confidence analog verification of functionality and performance and various other, concerns. But a lot of the system and, multi-chip systems can be well validated with real number modeling. But we can see a growing problem here, right? We are maintaining probably a wide number of models for different reasons, all the way up to probably a system C model, right? And it is kind of growing problem to make sure that they're all in sync and in sync with the design intent. Right? So automation techniques and a lot of data science applications in analog modeling, model management, and model validation methods are emerging, and that's really interesting for mixed signal folks. Safety verification is now and it's on track, right? It's a very focused track that runs alongside our functional verification. Automotive standards require us to follow a very high degree of safety considerations, right? And that's of course really critical for our end safety requirements. So it comes with the requirement tracking, functional safety planning, and execution being very critical in these projects. So what's the evolution happening here, right? So interestingly, the fault injection is not just about certain components, but it is about making sure that the architecture itself is robust, right? And we have to quantify the effectiveness of the safety mechanisms that have been put into the architecture. So the question now comes to, as our systems are becoming more bigger, how do we scale the speed of how we do these fault injection simulations, right? And of course, the safety validation across multi-chip standards is, multi-chip systems is getting to be also very important. And finally, the security of the system, right? As more and more communication is established from these intelligent devices to all the way up to the cloud, it is important that the security starts right from the edge. So trusted firmware and secure boot processes, key and product lifecycle management, the entire framework of security around the system, and of course the interfaces are very critical to allow only authenticated and secure traffic to and fro from the system. Security is really a highly a system focused effort because it's about verifying beyond what the designer wrote down in the specifications, right? It's about understanding potential system security loopholes and all the complex, key management that exists between all the components. We of course deploy all our new methods on formal for security frameworks, and there are emerging third-party compliance tests for a lot of the network devices. But the key here is that we have to operate from a system level when we think about security. It is about managing levels of trust that exist within the system. It is about testing for the weakest link in the system, because you leave one door open and close all of the others very well. That doesn't really help from a security viewpoint. So again, it's important to see the full system level security to really appreciate and be able to verify a secure system. So as we look at these kind of edge devices, we are now seeing a need for a multi-dimensional view on our verification capabilities, right? So it's about having tiers of verification to validate an edge system solution. So for engineers in this domain, they need to be verification technology expert, but growingly they need to be systems focused, right? And they should have the capability and the skills to collaborate across disciplines, right? Talk all the way to marketing, to architecture, to customers, right? And to the product and software team. So it's a very multidimensional skill set that is required to operate in a system verification domain. So what's happening is, as these full systems are shrinking to within devices, it drives up the growth of talent base in systems verification as a part of DV. So exciting times ahead for verification engineers. Thank you.
Thanks, Ashok, for that keynote. So first question that I had for you was, how do you think AI ML will transform verification? And I think there are so many aspects to it. One is, how do you think it will, what we need to verify will change? Also, how will AI ML assist us in doing all these different tasks that you listed down in your keynote?
Yeah. Maybe I'll get into the first part, which is maybe how do you validate an AI ML solution itself, right? So when we look at products which have an AI ML, part of it obviously is the hardware, and that can be well validated within our conventional approaches, right? It's a model-based validation, or with a control focus approach. So I think that kind of fits well within our approaches that we have now. But when we look at the overall solution as a system solution, it's software dominated. So the ecosystem that we are putting in place to enable a software plus hardware validation schemes like prototyping, or even modeling with, or even emulation, right? All of these things really would help in a system verification of the entire AI ML solution, right? So that's what we kind of currently look at on that side. Now, if we look at the other side of things, how does AML help verification, right? So that's really very interesting place. We know that our EDA vendors are, of course, coming in with solutions that accelerate the verification process itself, where and that's in places where they have access to the data, right? So, for example, coverage closure. That's something that the EDA tools have access to the information, and that can drive faster coverage closure, right? So I think we are already seeing efforts on that direction. Mm-hmm. But now, if you look at internally, our data that we have within our company is about our designs and the amount of log information, for example, that we generate right through our debugs and regression. So that's quite a lot of data, and that's something that is very amenable to accelerating some of the debugs and other techniques through AI-based approaches, right? So if we put in a correct model, I'm sure we can figure out certain patterns and look at optimization. So there are possibilities to accelerate that. And obviously, I mentioned about analog modeling, right? Analog modeling is definitely something that is very amenable to machine learning kind of approaches as well, right? So there are different tracks through which some of these are being internally looked at in different companies as well.
I have a question from the audience. Can you let us know when is a virtual system platform made available to the software team? And the second question is it also helpful to enable third-party software partners and customers for this purpose?
So, if it's a brand new platform, I think it definitely takes a few months to get to there. But I think we can definitely be sure that a virtual system platform is much ahead of the design, and that's primarily because the virtual platforms are developed using abstracted techniques, so they don't get into the details of the clocking or how the exact software, exact hardware is designed, right? So that kind of keeps the model similar to some degree, and makes it easier to abstract the way you code it. So that in turn reduces the bugs in a model, and also kind of reduces the time that it takes to create some of these abstracted, for example, systems models, right? So we definitely see that a prototyping based approach comes out much faster and enabling a software development, much earlier, so that by the time we want to tape out, we have to actually be ready and validate the software with our, emulation or prototyping other techniques, right? So I think it does really enable that whole process to kind of fit in with a typical IC tape out schedule. Right? So that's one part, and the other part is about how third-party software ecosystems come in, right, Shreya? Is that right? Yeah. Okay, so
That's right.
So in terms of third-party software, maybe there is obviously the prototypes are really valuable for us in terms of even delivering it down to, if we are working with a system integrator, they would also want to accelerate their development, right? So it's probably we are now in a position to even deliver prototypes to our customers, enabling them to accelerate their development as well, right? So if it's that, that's possible, and obviously we can work with other third-party software providers to provide models for devices that can kind of be used for a general purpose markets as well. So I hope that addresses that part. Yeah, it was very clear on that.
Okay, maybe if the person can reach out to you if he or she has anything further. I'm afraid we have time for only that much right now. If I can share my screen again. So thanks, Ashok, for that keynote and taking the questions. Thank you very much for being at the conference.